In lesson 3.1, we're going to look at the equation of a circle. And we're going to start with this question. How many points can you find that are a distance of 5 units away from the origin? And if you recall from geometry that a circle is the set of points, the set of all possible points that are equidistant from some given center. So if we're choosing our origin and we want to know all possible points that are 5 units away, this is going to be analogous to saying how many points on a circle can you find? I'm going to write that down. How many points on the circle with a radius of 5 can you find? And so we've got this grid here, coordinate plane, and I think I might actually be slightly off. Let's see if I can select the part I want. More or less. And we will extend this line. Okay, and so I want to find all the points I can that are 5 units away. And so if you think about this, you might quickly say, oh, I can count 1, 2, 3, 4, 5 on the x-axis in either direction. 1, 2, 3, 4, 5, and find these 2 points. So I've got a point 5, 0. I've also got negative 5, 0. Maybe I'll go up on the y-axis. So I've got 0, 5. Down on the y-axis, I've got 0, negative 5. So you get 4 points that exist on the axes. And then if you recall, you might know, oh, 3, 4, 5 right triangles. So I can go over 3 up 4, giving me the coordinate 3, 4, or I could go over 4 up 3, giving me the coordinates 4, 3. And you could repeat this process with negatives. You could do 3, negative 4, 4, negative 3, so on and so forth. But my goal is to end up with the set of points that is every single possible point. Because once I've filled in all these points, and I guess I could go ahead and say, oh, here I could do these ones and then these ones. And so this is my set of points that I can realistically come up with off the top of my head for a circle with a radius of 5. Beautiful. But what if I wanted more points? What if I wanted a point right here and I wanted to know what the xy coordinates are of that point? Or say I wanted a point right here and I wanted to know what's the xy coordinates of this point. How am I going to be able to figure out every single possible set of coordinates? And so one idea is if we choose an x coordinate, we could find its corresponding y coordinate. So for example, say I pick my x coordinate to be 2, and say I go over 2 and down here, or over 2 and up here, noting that we get 2 y coordinates whenever we pick an x coordinate, because there's 2 ways that the vertical line will pass through the circle. But let's just look at the bottom one for a second. We have 2, something, some y coordinate. And if we are clever, we can recall that we could use the distance formula, but that's really just the Pythagorean theorem. So if I draw in the radius of the circle, and if I drop an altitude to the x-axis, and I now have a right angle, well then I know that this leg of my right triangle must be 2. This leg is going to be y, and the hypotenuse is 5, because our circle is defined as having a radius of 5. And then using Pythag, I could just say a squared plus b squared is c squared. In our case, a we'll call the leg 2. So 2 squared plus y squared must give us 5 squared. 4 plus y squared is going to equal 25. Y squared will be 21. And now this is the point where we want to remember, oh, when we take the square root, we often want to make sure to do the plus or minus, because y is going to equal plus or minus the square root of 21, corresponding to the minus square root of 21 down here, but up here we also have a coordinate 2, and that's going to be the positive square root of 21. And if you put that into your calculator, you'll get 4 point something. But that's the idea. So using the Pythagorean theorem, using Pythag, we can actually plug in an x and get out the corresponding y. Or we could plug in the y and get out the corresponding x. But we can do even better. So we can take this relationship from Pythag and the circle, and we can write a relation for the set of every single possible point, because every point must satisfy a squared plus b squared equals c squared, where our c will always have to be 5 on this circle. So for this circle, I could say that my equation has to be x squared plus y squared equals c squared, but c is our r squared. And that's literally just the Pythagorean theorem. Our a, our leg, is just represented by the x coordinate. Our b squared, our other leg, is represented from the change in y, or the y coordinate. And our r squared is just the hypotenuse, which has to be the radius, which is 5, equals c squared. So c squared is r squared. So the general form for the basic equation of a circle, so the equation of a circle centered at the origin, is just going to be the Pythagorean theorem, but expressed using coordinates. So x squared plus y squared equals the radius r squared. All right, so that's pretty neat. If we use x and y in Pythagorean theorem, we can have a relation that gives us the equation of the circle. And note, it's not a function. For one, this fails the vertical line test. We can very clearly see that if I try to draw vertical lines through the circle, I cross in more than one point. So that should be pretty obvious that it's not a function. If I try to isolate y and say y was a function of x, I would get y squared equals r squared minus x squared. Y would be equal to plus or minus the square root of r squared minus x squared. But that's two things. That's y would either have to be the positive root of r squared minus x squared, or y would have to be equal to the negative root r squared minus x squared, which is exactly what we saw with when we had y equals root 21 or y equals the negative square root 21, because one part of this is covering the upper semicircle and the negative root covers the lower semicircle. Together, this represents the whole circle, but it's not a function, it's a relation. So that's good vocabulary to review and good to be aware of. Okay, so let's look at some examples here. And actually, for these examples, we want to sort of tie this back to what we've been doing on the coordinate plane, which has to do with trigonometry and angles. So I'm going to say, okay, let's say we want to know where the terminal side of some angle on the coordinate plane intersects some circle centered at the origin. Okay, so we're going to use trig to be able to do this. So let's take an example. Let's say we have x squared plus y squared is equal to 9. Okay, let's just use this example. And so that's going to mean I have some circle. The radius of that circle must be 3, because we know that x squared plus y squared equals r squared. That means 9 is the radius squared, c squared, right? It's the hypotenuse. So 3 squared is 9, making the radius 3. So I have a circle with radius 3, or in theory I do. I guess let me just draw one with radius 3. I think that'd just be better. So we'll go here, and then it's actually harder than it looks. All right, that was pretty good. If I had my tooting horn, I would toot my horn here, because that was not the easiest thing to do. But all right, so I got a circle with radius of 3, centered at the origin. X squared plus y squared equals 9 is the equation of that circle. And let's say I want to know where the angle of, let's say, where does the terminal side of the angle pi over 6 intersect this circle? And it might seem like a random question, but it's actually going to be a really important question. And we're basically saying when we say where, we're saying at what x and y coordinate does it intersect. So let's go ahead and draw this angle pi over 6. That's 30 degrees. So I'm going to start with my initial side fixed to the positive x-axis, and a 30-degree angle might look a little something like this, and I'll label it pi over 6. And the question is really, where am I intersecting my circle? What is my x and my y? And so we know some information here. First of all, we know that we can create a right triangle because that is really our best friend and one of our best tools. We know that the hypotenuse must be 3 of this right triangle. We know that the opposite is basically just going to be the y coordinate, and that we know the adjacent is just going to be the x coordinate. So I can actually use trigonometry to figure out what x and y must be. I could say that sine of theta is equal to the opposite over hypotenuse. In this case, my theta is pi over 6. My opposite is currently unknown, so we'll say opposite. My radius is 3. Now, sine of pi over 6, that is one of our special right triangles. That's a 30, 60, 90 right triangle. So if I have a 30 degrees or pi over 6, 30, 60, 90, we usually can express this with like y, 2y, y squared root 3, or however you like. But sine of that is going to be opposite over hypotenuse, which is going to be y over 2y, or 1/2, is equal to opposite over 3. But recall we said that the opposite is just literally going to be the y coordinate. So 1/2 is equal to y over 3. And we get y must be equal to 1.5. A half is 1.5 over 3, or I really prefer y is equal to 3 halves. So we found our y coordinate, 3 halves. And then we can use this to find the x coordinate. Take a moment to think, how would you go for the x coordinate? If you said use the cosine, you would be correct. So I can use my cosine ratio now, which is orange for some reason that I just chose. So cosine is going to be cosine pi over 6 is equal to the adjacent over the hypotenuse. Cosine of pi over 6. So pi over 6 is like 30 degrees. That's y root 3 over 2y, aka root 3 over 2. Adjacent is just going to be my x coordinate, and my hypotenuse is just going to be my radius of 3. Moving some of this around, we're going to get x is equal to 3 root 3 over 2. And so my final coordinates are 3 root 3 over 2, comma 3 over 2. And that answers where does the terminal side of this pi over 6 angle intersect the circle with a radius of 3 centered at the origin. Okay, let's do one more example, and that'll probably wrap us up. So let's see. Let's go and let's use an angle that's going to be in a different quadrant than quadrant 1. Let's say I have the circle. We'll call it example number 2. Let's say I have the circle x squared plus y squared is equal to 16. So first off, ask yourself what's the radius? And let's say that theta is going to be equal to 5 pi over 4. Okay, x squared plus y squared is r squared, meaning r squared is 16. R must be 4. So radius is 4. So I'm going to model my situation. Always a good idea to draw, model. So I go 1, 1, 2, 3. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. I didn't want to risk it this time. 1, 2, 3, 4. Even though I nailed the one with 3, you never can be too certain. So we'll draw, hopefully it recognizes I want a circle. Yeah. Good job, buddy. All right, and then get my axes in there. Beautiful. Okay, so I want to know where does the terminal side of this angle in standard position, this is all presumed, intersect my circle. So first of all, I want to draw my angle in standard position. The initial side is always fixed to the positive x-axis. The terminal side is going to be at 5 pi over 4 going clockwise, landing us in quadrant 3. Let's It's one of our classic angles. So that's an angle of 5 pi over 4 radians. And the question being asked is, what is this xy coordinate? And so we're going to use trig to find it. Let's draw our altitude, making our radius 4, or our hypotenuse 4. Our reference theta that we think about is in here. So our adjacent is going to be like the x-coordinate, and our opposite is going to be like the y-coordinate. Given all these facts, I can say that sine, which I like to start with for some reason, of theta is over h. Sine of 5 pi over 4 is going to be equal to, my opposite is the y-coordinate, and the hypotenuse is 4. And remember, this is an angle. Sine of 5 pi over 4, so that has a reference angle of 1 pi over 4, somewhere over here, right? Pi over 4 is my reference angle. Pi over 4 is like 45 degrees, so that means my reference here is a 45, 45, 90 triangle with x, x, and x root 2. So sine of 5 pi over 4 is going to produce a ratio of x over x root 2, except the y-coordinate is going to be negative, so it's going to be negative x over x root 2. Doing all that out, we're going to get negative root 2 over 2. If you're stuck on that, just put in a calculator for the moment, because that's not mainly the point that I want to show at the moment. So we get the sine ratio equals y over 4. Doing a little simplification, we get negative 2 root 2 is equal to y. Okay, so that's going to be our y-coordinate, negative 2 root 2. And an interesting thing about the 45, 45, 90 triangle is that the cosine ratio, the opposite and the adjacent, are both x. So cosine of 5 pi over 4, well, in this case, that's going to be x over 4, because the hypotenuse is still 4. The x is my adjacent. Cosine of 5 pi over 4 is the exact same thing, because we're in this negative, negative quadrant. So it's going to be negative root 2 over 2 equals x over 4, giving me negative 2 root 2 is equal to x again. So I get the coordinates negative 2 root 2, comma negative 2 root 2 is the place where I intersect this circle. So that sums up this lesson. It tells you the equation of a circle is x squared plus y squared is r squared. It comes directly from the Pythagorean theorem. And for that reason, in conjunction with the way we've defined trigonometry on the coordinate plane, where we're able to build these right triangles and have reference angles and do sine, cosine, and use the x and y coordinates, we end up with this system in this relationship. So I hope you enjoyed this video. Thank you for watching.